Hello everyone, and welcome back to the AI Research Roundup. I'm your host, Alex. Today, we're exploring an empirical study of Qwen3 quantization from May 4th, 2025. This paper examines Qwen3, a potent open-source LLM, and its performance under low-bit quantization. Low-bit quantization, that's a method to shrink AI models by using fewer bits for their internal numbers, boosting efficiency. The researchers tested several post-training quantization, or PTQ, techniques applied after model training across various bit widths, which is the number of bits per value. They found Qwen3 maintains good performance at moderate bit widths but degrades significantly at ultra-low precision, underscoring ongoing compression challenges. And for those interested in digging into the specifics, the authors have also shared the code for this work. It's available in a GitHub repository called the Qwen3 AI Qwen3 GitHub repository. Okay, so figure 2 here illustrates the zero-shot common sense reasoning accuracy. That's the model's ability to reason on tasks without seeing examples first, using per-group quantization of Qwen3 base. Per-group quantization means model weights are compressed in blocks, not individually. We see results for AWQ, GPTQ, and LLM. Across these methods, accuracy generally rises with model size and higher weight bit widths. As the paper suggests, performance is good at 8 and 4 bits, but there's a clear drop at 3 bits and an even bigger one at 2 bits, especially for these reasoning tasks. Alright, so after looking at common sense reasoning, figure 1 here shifts focus to perplexity, or PPL, using the C4 dataset. Perplexity, that's a common metric in language modeling, where a lower score indicates the model is better at predicting the next word in a sequence. We're again seeing results from those per-group quantization methods, AWQ and GPTQ, plus LLM across different Qwen3 base model sizes. And the pattern is quite consistent. Perplexity generally gets lower, so performance improves, with larger models and higher weight bit widths like 8 or 4 bits. However, when you drop to 3 bits, and especially 2 bits, the perplexity really climbs. For instance, at 2 bits, GPTQ holds up a bit better than AWQ, but both show a significant hit to language quality. The LLM method, which is a binarization technique, essentially a 1-bit approach, is also shown, and its perplexity is notably higher than the multi-bit methods. Okay, so figure 4 continues our look at zero-shot common sense reasoning accuracy, similar to what we saw earlier with per-group methods like AWQ and GPTQ. This figure introduces smooth quant, which uses per-channel quantization, meaning compression is applied more finely, at the level of individual channels within the network layers. Smooth quant also performs weight activation quantization, so it compresses not just the model's stored weights, but also the activations. These are the dynamic signals passing between neuron layers during computation. And we can see that this activation quantization seems to be challenging. Even at 8 bits for both weights and activations, there's a performance drop, and this drop gets worse as activation precision is reduced further. Alright, so figure 3 brings us back to looking at perplexity, or PPL, on the C4 dataset, similar to what we saw in figure 1. But this time, it also includes smooth quant, the per-channel method we just discussed for common sense reasoning. So for the per-group methods like AWQ and GPTQ, the story for perplexity is much the same. Lower perplexity with larger models and higher bit widths, with significant increases at 3 and 2 bits. With smooth quant, which quantizes both weights and activations, we see that even W8A8, that's 8-bit weights and 8-bit activations, shows a slight rise in perplexity compared to full precision. And when activations are quantized further, like in W4A8 or especially W4A4, the perplexity really jumps up, confirming that quantizing those activations is particularly tricky for Qwen3. To sum up our empirical study of Qwen3 quantization, it's clear that while per-group weight quantization down to around 3 or 4 bits holds up reasonably well, these models are particularly sensitive to activation quantization. Trying to compress those activations, even with methods like SmoothQuant, really underscores the challenge, often leading to noticeable performance drops. This research is valuable because it provides practical guidance for efficiently deploying these Qwen3 models, highlighting the specific trade-offs involved. That's all for this AI Research Roundup. Thanks for listening. I'm Alex.